Hello, class. Welcome back to the channel and welcome to this very new playlist. So, from this video onwards, we are going to start a very new module, or you can also call a new playlist. In this playlist, we will be discussing about the transmission line modeling and the performance of the transmission line as well. So, to understand this module, you must have basic knowledge of the principles of power system and how power system operates. You must know the basic concepts and basic operations of power system, which by the way we have discussed in the separate playlist of basics of power system principles. So if you haven't checked that out, if you don't know the basics, you can check that out the playlist. The link will be flashing on the I button on the top right side, top right corner of the video. So if you haven't, please check that out. If you have already, so let's move on with this module. So firstly, let me be very clear what we are going to discuss about in this module, in this video, and in upcoming videos as well. So we are going to discuss about the characteristics and performance of transmission line. We are also going to discuss like basically when we discuss the characteristics and performance, what do? We discuss about the efficiency and regulation of that transmission line, right? So what is going to be main focus of this playlist or this lecture series? It's going to be the relation between sending end voltage and the receiving end voltage, as well as current, both voltage and current. And we are also going to see the power flow diagrams on lines, and we are also going to discuss reactive power compensation of transmission line as well. So let's first start with transmission line. I'm pretty sure that you all already have some idea what is a transmission line. Even though, let me give you a glimpse if you haven't. So basically, transmission line is a line which connects generating system with distribution system. So generating system means whatever the generating station you are having. It can be wind, it can be solar, it can be thermal, it can be hydro, it can be anything, right? And the distribution system, when you distribute your electricity, so the link between them is the transmission system or transmission lines. So it is basically nothing but a set of conductors, you can say, and it runs from one place to another. It runs from generating end to distributing end, and because of that, it is having few different parameters. Based on that, we based on that we select our transmission line. Like every transmission line will have some certain resistance, inductance, capacitance, right? So based on that we select it. Again, the voltage and the current, they change harmonically along the line with respect to the distance of the point which is under consideration, right? And uh, there are transmission lines of different lengths. Okay, so there are so many transmission lines with so many different lengths available. So let's try to explore them one by one. Here we are having three types of transmission lines. First one is short transmission line. So the transmission lines which are up to 80 kilometer lengths, from 0 kilometer to 80 kilometer of length, are and the transmission line which normally operate under 20 kilowatt are generally termed as short transmission line. And the effect of the capacitance in such lines are extremely small, or they're that small that we can neglect the effect of capacitance here. Okay, so if you are doing any calculations for a short transmission line, you can avoid the capacitance calculations, right? We can neglect that. After that, then comes the medium transmission lines. So the transmission lines which have lengths between 80 kilometer and 160 kilometer, and also the line voltage between 20 kilowatt and 100 kilowatt, are known as the medium transmission line. uh, because this is not a short line, this is a medium line. There will be some capacitance effect, right? So because it is have some appreciable length and some voltage as well, so the charging current will be applicable, and as charging current will be applicable, we will have some capacitance effect, right? Then uh, over this line, as it is having a capacitance effect, so the shunt capacitance, we can assume it to be lumped in the middle of the line, or we can also assume it, if you don't want to assume it lumped or in the middle of the line, we can also assume it at half of the shunt capacitance we can consider on each end of the line, right? And based on that, we have two modes, or two different terminologies, which are called nominal T and nominal pi terminologies. And based on that, we can represent our transmission lines, which we are going to see in probably next lecture, or on after that. So that is your medium line. Then there is the third one, which is called long lines. So the transmission lines which have length more than 160 kilometers, and line voltage above 100 kilovolt, are generally termed as long lines or long transmission lines. So uh, by the way, these all the uh, classification, which is based on voltages and kilometers, it generally differs in different books. So if you are referring some other book, the parameters might change, the voltages, the distance might be different in those books, but generally we take difference somewhere close to 80 for short lines, 80 to 160, close to 80 to 160 in medium, and greater than 160 for long lines. In different books you will find different values, but it will be close to that. Okay, so it is okay if you considering a line which is having 81 kilometer as short line. Okay, it's the boundaries are very fuzzy here. Except for that, I would like to tell you one or two more things about that uh, transmission lines normally operate with a balanced three phase loads, right? We all know, from the generation to transmission, we separate our power with three phase, within the three phase terminology, right? And the sum of all the currents in a balanced polyphase system is always zero. Remember that. If you don't know already, the sum of the all the currents in a balanced polyphase system is always zero, and hence the current through the wire which we connect between the and star of the load and the neutral of your system is always zero. Okay, so current between the star and neutral is always zero. Any star point in neutral is always zero. And what does that means? So that means star point of the load and neutral of the system are at the same potential. Okay, they are holding same voltage value. So here we have shown the three phase system. In this image you can see we are having three phases R, Y and B. This is on the left hand side, this is my generator or generating station, you can say. On the right hand side I'm having my load. So as you can see, the load is RL load, or you can also call it resistive inductive load. So on all the three sides you can see resistors and inductor, and on the generating side you can see only generation side, generating windings, coils, right? Inductive things. And the line which are connecting them, see, R is connected with R, Y is connected with Y, and B is connected with B. So the lines which are connected them are transmission lines. And again, see, we are having resistive and inductive elements, right? So line is RL line, most of the lines are. Okay, and as it is as we are having connections like that, and as we are having balanced three-phase system, we can also analyze it like a single phase system. So for that analogy we have shown in the figure below here. Here we are having generator, we have shown it like a simple generator. There is a line between that and then there is a load connected, right? Pretty much simple. If you want to represent it with the circuit, if you want to represent this three-phase system as a single phase system, how do you represent it? We can represent it this way. You will having a generator, you will indicate this generator with E or G, whatever you want to indicate with. Then the sending end side impedance, and it will have inductive and resistive components. Then we are having line components. Line impedance will be called ZL, and it will also have resistive and inductive components. And here we are seeing on the right hand side is load component, and it is also having resistive and inductive elements. So we call the load impedance ZL. Okay, I think it is pretty much clear. Now let's try to move on towards the short transmission line calculations. So let's first let me repeat one more thing that wanted to repeat, that in short transmission line what happens, the shunt capacitance and shunt conductance are always neglected, okay, because they have almost zero value. Okay, they have almost zero value, so what do? We neglect them. Okay, now let's uh, let's come to the phasor diagram, let's come to the figure. So what will happen when we will study the performance of this line? We will only consider resistance and inductance, which we have considered here. You can see resistance and inductance, because what we are doing, we are neglecting the capacitance effect. Okay, and we have what we have done, we have drawn the equivalent circuit of single phase short transmission line, which you can see here. Okay, and the total resistance and inductance are shown as concentrated, or you can also call it lumped, because but in actuality they are distributed over the entire line equally. Okay, so the load we are connecting is connected over here. Load current will be given as I, you can see here. The loop resistance or the resistance of conductors is given as R here. Loop reactance is XL. The receiving end voltage is given as VR, sending end voltage is given as VS. Receiving end power factor, we will be giving receiving end power factor as cos phi R, and receiving end sending end power factor as cos phi S. Okay, so pretty much clear there. Here we are having sending end voltage, here we are having receiving end voltage, load is connected over here, and this is my line. This is the resistive and inductive elements of my line. Okay, now let's come to the phasor diagram. It is for lagging power factor because we are neglecting the capacitance effect, right? And either ways most of the systems you will be operating will have lagging power factor. Okay, so now let's see here what we have done here. We have taken the current I as a reference phasor here. So here you can see the current vector I is taken as reference vector. See, then what did we do? This OA line, this line, this OA line is representing receiving end voltage. Okay, which is given by VR. See, here it is given by VR, and it is leading your current by how much angle? Phi R. Okay, it is leading your angle by phi R angle, right? Remember always what happens, we are having whenever we consider lagging effect, lagging load, what happens? Your voltage leads your current. So that is what happening here. Then this AB line, this line, this horizontal line, what is it indicating? It is indicating the resistive drop, right? Or it is you can also call IR. And remember what happens with resistive drops. Resistive drops are always in the phase with current. Remember, resistive drops are always in phase with currents. So it is drawn parallel to OD, or parallel to the current component, right? Then another thing that here you can see BC. So what is BC? It is nothing but your inductive element of your drop, right? It is inductive drop. And remember, whatever whenever we consider inductive drop, your current will be leading by 90 degrees. So see here, we are having 90 degrees current. And uh, after that, we are having this OC, which is my sending end voltage. Okay. And one more important thing, see, sending end voltage is leading both receiving end voltage and the current. Okay. And what is the angle between current and sending end voltage? It is phi s. Okay. The angle between current and sending end voltage is phi s. Now I what do I want to do? I want to calculate the sending end voltage. Okay. So to do that, can't we apply the Pythagoras theorem on this huge triangle which we are seeing here, right? This triangle ODC, this triangle ODC, what will happen when we apply the Pythagoras theorem over this ODC? So can we say this hypotenuse, or OC square, is equals to OD square plus DC square based on Pythagoras theorem, right? So we have written it, OC square is equals to OD square plus CD square or DC square. Now tell me, what is OC? See, what is the value of OC? It is nothing but VS, right? Now what is value of OD? It is the summation of OE plus ED. What is the value of DC? It is summation of DB plus BC. So we have just written it. OD is equals to OE plus ED and DC is equals to DB plus BC. So that is our equations. Now let's come to every individual component. So first, can you tell me what will be the value of OE? If we take the cosine component of this vector, VR vector, wouldn't that be equal to OE, right? It will be equal to OE. So we can write OE as VR cos phi, and this ED will be equal to my IR, right? It will be equal to my IR because it is parallel. So what did we do? We wrote VR cos phi R plus IR instead of OE and ED. Now let's come to DB. So what will happen with DB is, so what will happen, this IR will be parallel to ED. So we can write IR instead of ED. So what we will write? We will write, let's come here. We will write VR cos phi R plus IR square. Now let's come to DB plus BC. So similarly, what will be the value of DB? So as VR, the cosine component of VR was equal to OE, can't we say the sinusoidal component, sine component of VR will be equal to DB, right? So what will be the value of DB? It will be nothing but VR sine phi. And value of BC is already known to us. It is I into XL. So we will just mention it. So what did we do? We wrote VR into VR sine phi R plus I into XL, right? Simple. And Vs was on the other side. So we wanted to find the value of Vs. So what we will do? We will simply take this square on the other side. So what will happen? It will be square root, right? So Vs will be equal to under root of Vr cos phi r plus Ir whole square plus Vr sin phi r plus Ixl whole square. Now what will be the percentage voltage regulation? So always remember, this is the formula which we use for the to find the voltage regulation. You will find this formula in almost every lecture of this playlist. You will see this formula very often, so try to remember it um, as quickly as possible. So it is nothing but difference of sending end voltage and receiving end voltage, which is divided by the receiving end voltage into 100, is your percentage voltage regulation. Now let's come to power factors past part. Let's see. I want to find the power factor of sending end voltage. I want to find the power factor of sending end. Okay. So what is the sending end angle? It is phi s. See, and I want to find power factor. So what is the formula of power factor? Cos phi, right? So cos phi s. We have to find cos phi s. So see this figure and tell me what will be the value of cos phi s, right? So the value of the cos phi s will be this OD, right? OD divided by OC, right? Now value of OD is already known to us. What is it? It is OE plus ED. See here, it is OE plus ED. And what is the value of OE plus ED? It is VR cos phi r plus IR. See here, the formula of Vs. So we will write VR cos phi r plus IR. And what is the value of OC? It is also known to us. It is nothing but Vs. So we will write Vs. So your sending end power factor will be VR cos phi r plus IR divided by Vs. Now what will be the total power which will be delivered, right? So it will be VRIR into cos phi r, right? Very simple, because what first did we do? We took this short transmission line. We represented the three-phase short transmission line in the form of a single-phase short transmission line, and now we are calculating the power. So what will be the power of single-phase transmission line? It will be VRIR into cos phi r, because we are calculating delivered power. So it will be the power of receiving end. So we will have VR into IR into cos phi r. Now what will be the losses? What will be the line losses? So it will be nothing but I square R losses. That will be your line losses, right? So the total power which will be sent out will be the addition of this total power delivered plus the line losses, right? Because what is the input? Input is always output. Input is always equal to output plus losses, right? So based on that calculation, power sent out is equals to VR IR cos phi r plus IR I square R. This is your input. Power sent out is your input. This VR IR cos phi r is your delivered power, which means that is your output. And this I square R are losses. So input is equals to output plus losses. What is your output? VR IR into cos phi r. What are your losses? I square R. The addition of both of them will be power sent out. Okay. Now tell me, I want to find the percentage transmission efficiency here. What will be the value of transmission efficiency here? It will be power delivered divided by the power sent into 100, right? That is the formula for efficiency. Now we have already calculated how much power has been delivered. Remember, power delivered was VR IR into cos phi r. So we will mention it over here. Then power sent out, what was the power sent out or the input power? It was VR IR cos phi r plus I square r. So we will mention it in 200. So that will become your formula for the percentage transmission efficiency, right? Now I have already found all these. Now I want to find the value of sending in voltage in simplified terms. Okay, I don't want all this square root and squares and all that complex things. I want to find it in easy way based on my phasor diagram only. Okay, so let's see how can we find it based on my phasor diagram only. So come here, look at this phasor diagram. So based on that phasor diagram, before we directly go to phasor diagram, come to this phasor diagram. Okay. Now, what we are doing here, we uh, we have taken what we have taken that we have drawn we have extended, actually we have extended this VR vector a little further. Okay, we have extended this VR vector a little further. Okay, so imagine we have extended it till here. Okay, and then what did we do? We draw a parallel line to that VR vector which will start from point B. Okay, so see what we have done. We have taken this VR vector, we have extended it a little, and then what did we do? We draw a parallel line compared to this VR vector which started from point B. Okay, so we drew that line over here. After that, what did we do? We drew a line which will stay perpendicular to the line which originated from B, or let's call it line BH. So we will draw a line which will be perpendicular to line BH, and the line, the other end of the line will connect to the point C. So we have drawn that, and based on that, this angle will be 90, right? Because we are drawing perpendicular line, so this angle will be 90, and we will draw this. And then the line which we were extending, we will only extend it till that line will land on this CH line. Okay, and at the and when the extended line lands on the CH line, we call that point F. Okay, we will call that point F. Now can you tell me, based on that, this OC, wouldn't that be equal to my line OF, right? Both of them will be equal, right? Now I want to find the value of OF. What will be the value of my OF? Will it be OA plus AF, right? We are just taking addition of these two vectors, vector OA and vector AF, right? Now what is vector AF? It is addition of vector AG plus GF, right? So we will write what will be the vector OF. It will be summation of first vector, this vector OA vector, so it will be OA plus AG plus GF. So what did we do? We just mentioned it, VS equals to OA plus AG plus BH. Now tell me, what was the value of OA? Right, it is mentioned over here, it is nothing but VR, so we will write VR. Now what will be the value of AG? What will be the value of AG? Okay, so to know the value, first come here, as we are only extending this vector a little further and we are not making any changes in the in its inclination or in its angle, and as this line, this IR line is completely parallel to OA line, wouldn't this angle will be similar to this angle, right? Because we are, what we are doing, we are actually constructing or fabricating this triangle, this angle here. So this angle will be nothing but equal to phi r. This angle will be phi r, and based on that, if this angle is phi r and this is my IR, can you tell me what will be the value of AG? The value of AG will be nothing but IR into cos phi, right? IR into cos phi r. So you now have value of AG. Now let's see what will be the value of this GF. Okay, so as this GF is completely parallel to this BH and the length of them is also equal, what does it means? It is equal to this BH, right or wrong? It will be equal to this BH. And now let's coming here, what will be the value of bh? We have to find the value of bh. Okay, now tell me that we have extended this line over here, right? So it is having uh same angle as phi r, and we have taken line parallel to it over here. So now see this triangle, and see this triangle. Can't you tell me this angle will be phi r, right? This angle will be phi r. See what is happening here. We are having this in this first triangle. Imagine this a and I are connected. If they were connected, this will be a triangle, right? And uh, here we are having angle phi r, the angle between uh, current and voltage, right? Same thing we did here. Here we are getting again the angle phi r, and here we are also getting the angle phi r. How? Because see, we took this triangle, we took this triangle, and again we took this triangle, but this time we just tilted it, right? So this angle will be phi r, and based on this angle, as this angle is phi r, the value of this bh will be equal to ixl, which means this component, and into sine phi r, which means it will be sine component of this, right? ixl sine phi r. Now we will add all of them. This OA, the value which we found, then AG value which we found, then GF or BH, both are equal, the value which we found. So when we add all three of them, what we will get? We will get Vs is equals to VR plus IR cos phi r plus IXL sin phi r, and that will be the value of your Vs. So that was the standing and voltage of short transmission line, single phase short transmission line. Now in the upcoming lectures we will say we will try to find the same values for medium transmission lines, and in medium transmission line we are also having few analogies which we will be discussing, pi analogy and t analogy. So we will see that as well. So let's keep this lecture till here. I will be seeing you in the next lecture. Meanwhile, if you have any doubts, any queries, or any questions you have, you can share it in the comment section below. If you have any feedbacks or any inputs related to video or playlist, that also you can mention in the comment section below. I will try to answer them as quick as possible. So I will be seeing you in the next lecture. Thank you very much for listening. Goodbye.